Welcome back, ladies and gentlemen. Today we're going to tackle section 12.4, Volume of Prisms. As always, there's your exit question on the screen. First off, a definition. Volume, I don't know if we've talked about this yet, but volume is the amount of space occupied by an object. And the goal when trying to figure out how much volume a particular object takes up is to chop it up into little bits. As you advance into mathematics and go into calculus, you'll chop it up into infinitely tiny bits. But for now in geometry, we're going to chop it up into 1 by 1 by 1 cubic inches or cubic units. It doesn't matter which those units are, centimeters, feet, or meters, but you're going to call it a unit cubed or cubic meters or cubic feet or cubic whatevers. But the idea is to try to count them in as efficient manner as possible. For instance, if I asked you not how many cubes are in this whole solid, but if I asked you how many squares are in this grid, you wouldn't go count each one, 1 through 18. You would say, hey, there's 6 by 3 here, and you would multiply the two together to count the number of squares. Well, likewise, when we are dealing with the volume of an object, we're going to try to count those cubes in as efficient of a manner as possible. So first, a couple postulates. Volume of a cube postulate, which basically just says the volume of a cube is the cube of the length of its side, which means that we can count things in cubic units. That's basically what that says. Remember, we had that length postulate and the area postulate, which basically says that we can measure things in length and we can measure things in area. Well, this one says we can measure things in volume. Postulate number 28 says volume congruence postulate. If two polyhedra are congruent, then they have the same volume. That makes sense. As does postulate number 29, volume addition postulate, which basically says that if you have a complex three-dimensional shape that you can break it up into little bits and add them together, like this one, like this would be a cylinder and half of a sphere, and this one is one with negative volume, or something where you take a large cylinder minus a small cylinder to find the volume of just the tube. Let's talk about calculating volume for something simple, something that you already know. You're probably well aware that the volume formula for a rectangular prism is length times width times height, or base times height times depth, or however you want to talk about it. But take the three numbers and multiply them together. Well, why is that the way it is? Well, what we're trying to do here is we're trying to count the number of cubes. And like I said before, if you were to count the number of squares up on the top layer, you wouldn't count each one up to 20. You would say this is, hey, a 5 by 4 grid. 5 times 4 is 20. Therefore, there are 20 square units up on the top of this face. Now, let's just take those 20 square units and grow some depth to them. So just grow them a little bit so that they're 1 unit tall as well. That would mean that we have 20 cubic units. And that would form one layer of this rectangular prism. Looks like that. And then once we had the volume of one of these layers, we simply have to count how many layers we have. Just like here we were counting the number of rows and columns, this time we're going to count the number of layers. So here a layer is worth 20 and we have 1, 2, 3, 4 of them. So we can split this rectangular prism into layers that are based on the area of one of its faces, which is kind of cool. Specifically, its base, if we want a view of this rectangular prism as having a rectangular base. Likewise, we can do the same method with a little bit more complex shape. I can take this triangular prism, for instance, and I can chop it up into 3 equal layers that have a depth or a height of exactly 1 unit. So when I count the area of the face of the triangle, I'm actually counting in cubic units. So if we look at this, if I wanted to find the area of the face now, I can't count these precisely because there's partial units here. But I can find the area of the face and then just know that it's 1 unit tall, so I'll have that. So this is a triangle, 1/2 base times height. So you've got base, which would be 4 units, and height, which would be 6 units, which means that each one of these is worth about 12 cubic units apiece. Add those all three together, and you get 36 total cubic units for the volume of the triangular prism. This idea can be extended to any prism, any right prism. So if we were asked to be found, if you were asked to find the volume of this prism right here, you would count the number of square units on its base, 1, 2, 3, 4, and multiply by how tall it is to figure out the number of total, or the total number of layers, or how much volume is in that entire stack. Likewise, we've got another triangle, base times height times how tall it is, or you can count the square units. We got 1, 2, call that 3, and maybe 3.5 or 4, somewhere in there. And they can get even more complicated. You know how to find the area of a regular polygon of any sides now. So we can give you a prism and an apothem and a perimeter and a height, and you'll be able to find the volume of the prism just by figuring out the area of the base and then multiplying by how tall it is. Again, you could count square units there to figure it out. And it doesn't even need to be a polygon. You can do this same thing with irregularly shaped prisms. So if you knew the average depth of a lake, for instance, was 10 feet, and you knew the approximate acreage of that lake, you could figure out the total amount of volume in the lake by approximating it. But here in this case, if I told you that the area of this base was, say, 10 square units and it was 10 square units tall, you just take the area of the base times the area times the height itself and get a total volume of 100 cubic units. So it breaks down into this sort of way. The volume of one layer times the number of layers, which basically means take the area of the base times the height of the prism. And for some specific prisms, that gives you some specific formulas, like the volume of a rectangular prism, which, or any prism, for instance. Remember that capital B stands for the area of the base. So for a rectangular prism, that would be length times width times height. I'm going to use a capital H for the height of the prism. I'm going to do that because little h for me is going to stand for the height of a trapezoid or a triangular face of a prism, specifically the base of it. So I'm going to use a capital H whenever I work. The book uses a little h there, but it's the same thing. And cylinder, same thing, the volume of the base, but this time the volume of the base is pi r squared. So whatever shape the base is, find the area of it, and then just multiply by how tall it is. Again, you can do that with irregular shapes. This is the general idea. Okay, then we go on to a principle, and I have no idea how to pronounce that guy's name, but he was fairly recent. And he basically had this idea that said that if two prisms have the same height and the same cross sections, then they must have the same volume and cross sections at each step of the way. So wherever you move this plane that's cutting the cross section, if the cross sections are the same between two prisms, then they must have the same volume as long as they have the same height as well. Pictorially, picture a stack of CDs or books or pennies or whatever. This stack of CD cases here has a given amount of volume, whether you stack it straight up or you slant it over to the side to make an oblique prism. It has the same amount of volume no matter how you rearrange the objects. Same with this stack of pennies, one that's nice and neat in a little cylinder and one that's skewed all over the place. These two stacks, as long as they have the same number of pennies in them, have the same volume. So you can make pretty complicated shapes like this and yet still have the same volume. So this is one with a square prism that's just been twisted. It has the same volume. Think of like the candy Twizzlers candy. If you tighten the spiral or loosen the spiral on that piece of candy, it still has the same volume. You haven't done anything to add or subtract from its volume. And then there's some weird stuff. So actually, this one's not so weird. This is just a right triangular prism versus an oblique triangular prism of the same height and of the same cross section, so they will have the same volume. Here's a pyramid that's set up in kind of the normal way of thinking about a pyramid, and here's one, the same thing, just all the little square layers are shoved over to one corner. And then you can get into some wild stuff that takes, as long as it has the same cross section all the way through, you're good. This is just makes kind of a wavy, continuous blob thing, but it has the same area as the more ordered one on the right. All right, so the basic idea here is if you need to find the area of any prism whatsoever, even if it's kind of funky and oblique or right and oblique, whatever, if you know the base of it and the area of the base of it and its overall height, you can find the volume of it. So in this case, I know the area of the base and I know the total height, so volume is 120 cubic meters. Example time. Here's a problem. Pause the video, see if you can handle it. It's a pretty easy one. Volume is base times height. The base in this case is a right triangle, so you've got 1/2 base times height, and that's little h right there. And then big H is the height of the prism overall for a total of 180 cubic meters. And there's your assignment for the day. I'll see you next time.